Why don't we go ahead and get started? David Bell, USRA Director for NASA Academic Mission Services. Just wanted to make a couple of announcements here. If I can page down. There we go. Where's the other slides? There we go. Okay. So what we started in collaboration with NASA and Berkeley is the Aviation Data Science Initiative. The seminar series is one piece of it. If you search USRA Aviation Data Science, you'll see the list of upcoming speakers as well and the video recordings from past speakers. But also we're launching courses. So there's a short course that we're going to have on campus at NASA Ames for on-site contractors. That'll start March through May. It'll be a 12-week course, combination of lab and lecture. The syllabus is online. There's handouts in the back. Registration is due February 20th. So if you're interested, please go online and register for the course. There is limited enrollment, so there's certain prioritization, but please go ahead and register, and then we'll get back to you about that. And Berkeley, we're collaborating with Berkeley also on creating a new course in the fall for aviation data science with Professor Raja Sengupta and Professor Mark Hansen. So please, that'll be upcoming for the students up at Berkeley. We are also, for the students up at Berkeley, we have internship opportunities and employment opportunities, so please go ahead, look at Handshake. For the internship opportunities, you can search for NAMS, and you'll see our listing there, and then USRA Careers. With that, I'd like to move into introducing Professor Marta Gonzalez. Marta is an associate professor at UC Berkeley with appointments in both civil and environmental engineering, as well as city and regional planning. She's a busy person. She's also a research scientist at Lawrence Berkeley National Labs and a former associate professor of civil and environmental engineering at MIT. I'd like to welcome Marta, who's going to talk about urban computing for planning energy efficient and healthier cities. Welcome.
Thank you. Thank you very much. Can you hear me well? Both in campus too? Can you hear me well? Great. Yes. So, needless to say, it's a great pleasure to be here. Now we are relatively closer. I've been 2 years at Berkeley. And I'm looking forward to research opportunities and collaborations to have students coming and going and doing very interesting things together. I put two pieces of work, as the title said, is urban computing in two different aspects. One is energy and the other is healthier cities. So basically, they say we're in the information age. It means we gave up our privacy to be completely connected in access to information that leave digital traces. Then this amount of data allow us to have a complete new way to see how different layers interact in the planet. Let's say we can see social interactions, traffic, energy, plus the map revolutions, we can see urbanization, etc. So similar to the NASA Earth amount of data we have, now we have it on the surface thanks to communication technologies. Then today, I'm going to tell you in detail how can we use mobile phone data, maps and census, together with electric vehicles, charging station data, to plan the adoptions of electric cars. In the second part of my talk, I selected a project in which I use a lot of NASA Earth data towards the prediction or inference of air quality on the surface. They're very different. The first part, I spent 10 years working in the mobility models out of mobile phone data. The second part has 1.5 years funded by the LBNL. It's ongoing work, is opportunities to work. At the very end, I make you some perspective and motivations about the urban air mobility. Then, here we have, what we have there is one of the several commercial software that allow us to have traffic demand models. And there's different flavors. The aspect of these models is that you need to have some input data, ground truth, about what the people do in a given city. You need to synthesize the population to count for everybody, and then they are based on activity generation, route planning, you do simulations, you calibrate, you have the results. That feedback is what is the so-called transportation demand models. One of the bottlenecks that make this work so hard is the type of input data. The input data for that has been, in general, travel diaries. It can be travel diaries, paper and pencil, and even now some cities can do it through the phone. They ask you where you go. The detail is that this actively collected is not like our Google Maps and apps that passively collect our trajectories. Then what I spent some years developing in my lab is how can we do urban models about which, by that I mean where and when and in which mode people travel with all the other data sources that are not actively collected. So without asking, we are leaving digital traces. It can be the easier, that is a smartphone, but even can be social media data, mobile phones, and credit card. What is the challenge? We need that data is representative of everybody on your city because you're doing demand models. And these data sets are sparse, very sparse, right? You only have the coordinates of the person when he or she uses the technology. You will see some of the details. We do not claim that every time you have enough information to build a model of someone, but that is part of the challenge. So how to create an individual trajectory with sparse and not representative data. So in a keyword, what we did is adapt the method to the data at hand. We would not assume that we would know why the people move. We would not do the typical agent-based activity simulator. What we propose instead is a complex system approach to find probabilities and rates about how people move. So we needed to somehow create innovation, and this approach comes from statistical physics of complex systems. Then, let me tell you a story, navigate you briefly through the aspects of the model, and let's do the model first with a control experiment. It's still passively collected, but it's 800 students in Denmark that have the smartphone data, as any smartphone data or app company has. Then we're going to build a model with these students. Then I'm going to use a commercial triangulated mobile phone data to model Boston, and I'm going to show you the differences and similarities in the model. I am not, don't worry, it's not an exam at the end of this, it's not homework based on this. All the details is in this PNAS 2016, but I want to give you the flavor. The flavor is that people have universal patterns, that is the circadian rhythm. You can see the probability of departures of everybody. And then you have heterogeneous patterns, that is number of departures you see somebody, weekly departures, rate between exploration and returns, and how long you stay in places. Even if you don't have every minute of somebody, you can have these rates. It's going to be an exploration. An exploration is a location that I saw the first time a person in. A return is your home, your work, your gym, where you have gone more than one time. Then the type of models work for every 10 minutes. We need to decide, is the person going to stay or is going to move? Then one of the hardest is when the person is going to go to a new location, where is going to go? There is no machine learning that is going to learn from something you never saw in the data of that person. It's a first location. For that, we use the maps that have a density of point of interest. It turns out that depending if your exploration is a other type of activity, commercial activity, you can guess what the person is going to be. All this field is called human mobility patterns. It was not one paper, was 10 years of work, not only of my lab. And then we have here one framework that produces this type of results. This is one student of the smartphone data. You see his simulation and his predicted locations. See, for a computer science type of prediction is low, because I am telling you, I can predict, then this is not when you are staying the next minute, and then if you sleep 8 hours, I predict perfectly. This is when you move, if I predicted your destination correctly or not. Because the students in Denmark have 70% of the locations are visited once, it's okay not to predict perfectly. However, let's see, our goal is planning purpose. This is my own student with commercial Boston data. What we can predict, we can have the person and the synthetic version of himself or herself, and we can predict in 6 months what is the histogram of daily visited location. My student, good news, is a commuter. He most of the days visit 2. Sometimes, because he did internship, and this was the summer, no, this was a year, because he has vacation included, he visited 8 locations. Then how long he stay in each of these nodes. These are the histograms of the typical days. They are the so-called motifs. Then we can create a synthetic version of somebody is weighted by the places we see him or her, the preferential return of the phone data, and we can model the explorations. We also have things like the frequency, the fraction of time visited in L most visited location. This means the first 3 is most of the time visit, and some other locations visited sporadically or only once. And of course, if you are waiting with the location he or she is in, you can have the distance, the probability of a distance travel, you fit pretty well because it's mostly driven by home and work. We can do that for commuters and no commuters, and the data is available to anybody to reproduce this type of models. An example of a company is Cubic. You can purchase this data for research purposes. And this is a new generation, I think, of activity models based on this passive data source. It requires some cleaning. So basically, the states need to be parsed. Then one part is parsing trajectory, then the modeling. Once we did that, just to give you a flavor, in the left-hand side, we have the sensible DTU users. In the right-hand side, we have AirSage, that is triangulated phone data. One looks way cleaner because it's many more, 2 million users. In the left-hand side, we have 800 students. The rates are not the same because this is a subset of the population is a student. This contains everybody. We can do this rate by census tract, meaning people tend to explore more or less depending the income of your census tract. It can be several flavors. But the important thing is that we can extract the rate for active users, that you have enough information. And here I have an example of a 30 days user here that only have 10 records. But still I could measure home and work of that users. Can I generate a model with him or her? Yes, we can. That's why TimeGeo or the framework is useful for. You learn the rates and then you don't claim that is the person. It's a synthetic version of the person. And at the end of the day, what is the advantage? That we are using 2 million users to feed the daily mobility, then the traffic models to calibrate that versus only 30,000 people that the city interviews, we have way better chances to calibrate our ODs. Then that makes our life much better. And then we just got validations by the commuting transportation planning package. We can assign this model with simpler or more complicated traffic simulators like Sumo, but at the end of the day, what we provide is, from the phones, travel demand. What keeps me absolutely engaged in this is that some of the users are actual people that have the phone. Then we can plan something from the city and send information back to them, of course, in agreement with the companies. Then in this realm, I use this framework to plan for the electric cars mobility, because a lot of work was going into improving traffic. To improve traffic, you need less cars. You change the route, but that is harder, you know? Taking the people off the car is not what the model is going to be, really. And then one of the impact I thought is, let's plan for something that's not there yet. That is the EVs. It's not massively there. And because the motivation is clear, apparently it's happening. Several cities and countries are going all electric for all the reasons we know. Then to do that, similar to all the work I do, I start data-driven. So we got access through the LBNL collaborations, easy charge. Those are one company that tells me the user ID, let's say in pink, when he or she was staying in different, through one day, in different charging station. And then we have him in another charging station here. So basically, we can know the trajectories of the EV through the charging station. We only got 15,000 vehicles just to see some patterns of the charging station data. And the challenge, and this challenge is going to happen for the EV adoption and probably also for the air, is that people is going from their cars, few of them are electric. In this case, we're analyzing the consumption of energy of one charging station, only one, that have 450 vehicles. Notice when they arrive, just after the commuting peak. This huge peak, this is only 450, but if we have a big fleet of our cars go electric, that's going to be very hard to handle for the power grid. This is an active research topic, and I was discussing with someone in the morning, what if when we have the charging, the urban air is going to be even higher? So the power grid needs to adapt to this. Then the challenge is that the EVs are going to charge in the grid. I only have 15,000. I would not plan demand energy for 15,000. What we did is, let's do what is the probability that I have an EV given my mobile phone data model in which I can impute the income based on where they live, is an imputation, and the distance they travel. Those two I can know, and I don't know who the EVs are, but we do this approximation, the second one. These two, what is the typical income of the EVs and how long they travel, is taken from a survey. So we still need surveys, right, to know the behavior in terms of the EVs. We know that it's only 0.62% of the cars in the Bay Area are EVs when we did this work. And this is the typical distribution of my entire population. Now we can go from my simulated to, of course, we validate in the car vehicle rebate program, that is another data set, that when you bought an EV, you could register that to get a discount. Then, for example, in the Bay Area, when we did this work, that this was already 1.5 years ago, one zip code that have more EVs living in there have 250. But the important thing here is that we started with 15,000, and then we expand to have the model of the current EVs. Then we can go into a optimization objective, that is the peak demand. I want to minimize based on what? This matrix I have are all the users that are serving one charging station. Then I have where did the mobility come from. I have the arrival and the departure, and the charging station depending on how much your car needs to be charged. Instead of making the old-fashioned way that you come, you charge, and you have all this moment, that's why we have the peak, the green part, you can shift. And that is all this shift we do. The detail is, every customer of the charging station needs their car to be charged by the time they're leaving. That's in the part in which we need to know the mobility to be able to shift these charges, adapting to what the people have. Of course, if we shift in 15 minutes, we don't gain so much. If we shift in 30, at the end of the day, we can change the peak, changing, playing with the departure and arrival of the charging data into my time up to 1 hour. This amazing one, if you have new technology in which it's not about when you charge, but you are there and then you can play better so basically the charging time do not depend when the person arrived. In this case, we are managing departures and arrival to the station. If the person arrives whenever they want and you can charge and switch that, much better safe is done. So this is a new technology that our charging stations do not have. This is playing with recommendations to the travelers. We had the data in a 2018 paper. The whole mixed integer linear programming was by Scott Mura and Emre Kara, that were collaborators with Jan Scherder and myself, that is the mobility hat experts. Then we can do the benefits. So basically, with this changing in your schedule, based on the better peak, you can have other access to the tariff, and then this can be translated to monetary benefit. This monetary benefit is for my 150 car station, charging station, and it's for the entire month. What this means is that the amount I'm saving right now is like a coffee per day. Would you change your commuting time for a coffee? Not necessarily, right? That is one of the challenges that we face when we do demand, that at the end of the day, similar to dropping your car, changing my charging, my arrival behavior, it's gonna depend on the people accepting or not the process. So if this would not be a talk for NASA, there is a whole field that has to do on the adoption of people. It's more the business school type of research. It's called computational social science. At the end of the day, everything has to do with the adoption of behaviors. And here I'm showing, for example, the phone data is also who called who, and they have communities. And in the down, I'm showing we could track with Twitter data how Twitter came from 80 people to 3.5 million. And it's a whole adoption, but now we're all talking about adoption of new technologies. The other plot here is adoption of the TV, of the phone. All these things are adoption processes. What we like to apply is computational social science in the urban domain for recommendation. That is one field that I see as an important direction, because it's beyond collecting data, having the demand, and then how you convince people to do for social goods. That is either traffic or energy. Overall, this field tries to do policy-informed decisions by science and engineering. I show you an example that couples energy and mobility. This is ICT, stands for Information and Communication Technologies, environment. So this is a piece how we go from the data to the demand model to a purpose. Now, going into the environmental part, this is, compared to the work I showed you before, this is relatively new. It's a baby from the lab. It's 1.5 years old. Stay with me. But it was a lab-directed research fund. So it means it was a good enough idea, and we are on board. People from my group is Jan and Dimitris. Lin Jing and Thomas Kirchstetter are experts in atmospheric chemistry. So I would not go into the topic and learn all over atmospheric chemistry. We have in Berkeley an initiative that is called the Sustainable Transportation Initiative. They have been doing several things. It was an opportunity to go into the environment. So transportation consumes, we already know, 30% of the energy, however also emits 50% of all NOx, black carbon, and pollution to the US. We are not in the situation of cities in India and China, it's okay. However, it still may be an issue, and we are working into this area. And the opportunity is applying state-of-the-art artificial intelligence technologies, in this case is called deep reinforcement learning, to transportation and environment. So it's very general. And it was motivated with a project I had really with air quality in Beijing. Here is Beijing, here is 2 p.m., same place. It should look like I could see the building, and I don't see the building here in the back. These days in Beijing are called the haze days. It's really bad. And it's a combination of human activity, the plants, the traffic, but they are there every day, and the environmental, the weather. So it's a combination of weather, which is fascinating with my statistical physics hat, that this combines completely two scales of temporal activity and spatial activity. So the people and the environment. It's very interesting to do research on. This is an example in Beijing. We started in Beijing, and I realized how hard it was to predict the air quality at the urban scale. So then I moved to Berkeley, and in the lab, we were funded to work on this, just to be sure what we're going to predict to begin with is the PM 2.5s. Those are particle matter of 2.5 micrograms per meter cubic, per cubic meter. Then, to tell you an example, if I tell you that the PM 2.5 is 22, that is equivalent of 1 cigarette per day. Then we are not too bad in the US average. However, look, Beijing in a haze day. It's really complicated. You can have your kids, your grandparents, like they would be smoking. So bad is there. This is equivalent in research, in health aspect. Then for the case of Beijing, the type of things you can do, and that we can do anywhere, this is a sample paper, we can do exposure. And that is what we did at the end. When I realized how hard was the prediction, we would say, you can have a web page like this that tells you, if you go from this dark blue is the census tract you are starting, and at the end of the day, this is the amount of PM 2.5 that you're going to be exposed if you go from here to all the way to here. Of course, if you would be biking, but this is just how bad it gets based on how you move. Then, again, mobility-based, we were showing, depending where you live, and notice it's not completely symmetrical. You have to do with how the air and the winds goes. So the typical thing we have is the monitoring station, for example, for Beijing are here in the white point. We had the mobility without traffic, with traffic based on phone data, and we measure the exposure. Then in the LBNL, we wanted to go one step forward. Is Department of Energy funded. We move the same challenge and problem to the US. We are not working with Beijing data, is the DOE founded. And what we propose to them is gather all the data and apply our platform, develop this platform that allows me, this is the goal, and I'm going to tell you where we stand right now, but the goal is I can label zones where I do not have monitoring station according to their quality. Of course, right now I need the monitoring station to validate the model, and that's what I'm going to show you, how the model stands right now. So basically, the innovation is that we have multi-scale images, computer vision techniques, and the idea, this is the final goal, beyond the prediction exercise, how we can inform either transportation policy or the atmospheric chemistry model. So beyond a prediction exercise, we're going to go a little bit further, but for now, we are on the prediction. When I said about the atmospheric chemistry models, and I told you about the different scales, is because you have PM, particle matters, relative humidity, planetary boundary layer, and secondary planetary matters. All this you have data on. And in atmospheric chemistry, they know that when things change due to weather conditions, there is a way that things happen and the haze events generate. This has been done in typical AGU papers, and this is the type of knowledge that Ling and Thomas give us. So we would like to understand the atmospheric chemistry of the process and use the data available to predict. To tell you an example, this paper is 2016, and here they are, typical. In California, that is where I'm going to show you where we're doing the deep learning model, we have these grids. Then you have what is the PM 2.5 in grid IJ, and you have several variables. Aerosol optical depth, the basin it belongs to, relative humidity, wind speed. Is a linear model. And the type of only using AOD that is very related to how bad the air is not enough. Then the best, with a relatively simple model, the best prediction they can have is with an R square of 0.66 in California. Then in that context, we thought not to have complete faith on the complicated models, but we thought this is a good example for it's so many parameters and different scales and temporal scales. We thought this is a good candidate of problem to try a deep learning model. So basically, we have the data on meteorological information. We have the aerosol optical depth, the mass images, I'm going to tell you a little bit more about that, the elevation, the emissions, and at the end of the day, it matters the basin, the weekday, and the month. So we put all this data together. We have these networks. And when we go into detail, at the end of the day, right now, in the first try, we have our monitoring station here. And we have this 100 by 100 kilometers where we have all the data available. And we put state-of-the-art trained prediction model. One aspect we learn on all this, instead of having so much information on land use, distance from the highway, so on and so forth, we discovered that just using the images in the grid of Google OpenStreetMap or Google Maps, it tells you a lot. So the model surprises us that, and if you think about it, because they are going to see if there is a highway, they are very good in images. So just using map images instead of other data sources that come from the Federal Highway Administration work much better in the CNN model. One challenge we had, the AOD, aerosol optical depth, is missing in many of our grids. Then we really need to do deal with that. A lot of complete information data for these models to run. And at the end of the day, we have a benchmark model would be the gradient boosting machine. You have training and testing. See, it's not so good. And right now is the DeepAir testing. Notice I mentioned in California, the previous paper is 0.66. We are only in 0.60. That's okay. What took us all the time is putting the data together and do the first run. And now we need to go more details into improving this totally. It's a work in progress. I'm sure we will improve on this 0.60. However, imagine we have the best model and we predict 0.89, meaning in the stations, in the places I do not have a station, I can tell you my best what the air quality is. Part of the message I want to tell, and in fact, January 15, less than a month, it came this paper with the group from New York that has been a long time working on that, tackle our same problem. Right now they have with random forests, 0.6, so they are using purple air. If we have not purple air and we are predicting a spatial, they have 0.81. It's almost typical computer science paper. It's the competition for the prediction. You have benchmark and variant prediction. However, I come civil and environmental engineering and planning. We are going to go beyond the prediction. And I want to share with you the type of challenges we have after we can predict the air. We can to really inform transportation planning to see if you do this, this is going to happen. And other type of problem we would like to do. For the understanding, postdoc did DeepAir, and I have my PhD student, and we followed this fantastic paper. It's called, it used a network approach to study and quantify the spreading and diffusion patterns of air quality. He did it in China, entire China. And what I want to put in these nice figures is it must be an intuitive understanding of what's going on. If I tell you the R square, it's not enough. I want to learn better why things are working as it is. Just to take you an interesting result, we are doing the time series of the PM 2.5 in the different monitoring stations. We have 160 in California. You can measure the spatial correlation between the PM 2.5. To our surprise, you have positive correlation. It makes sense. There is bad here, there is bad there, and it goes. And you do this in different tau, that is time stamps. But it is negative correlations. And the different here is the different December, January, February, March, April, May. So different station, you have this. This is the slow-mo Havlin results in China. We have this in the US. And then we can see what is the temporal stamp of the correlation. Then the negative correlations are surprising. And they may have to do with event, which means it doesn't matter what happened in your station, in my station, it's completely different. So they are not positively correlated. It's something strange. So the positive correlation have similar patterns both in China and California. And the negative would tell us something. And at the end, what we do is this, I find this fantastic, that we create a network depending on the threshold of the correlation. And we do the unitary vector that is connecting the correlation between the two stations. Then we have, for the winter months in China and California, this direction on the correlation of airs. Then This is only using the time series of PM2.5. What would happen if we start using other time series, other events? This is a complete different approach, complementary to the deep learning, such that we can gain understanding. The Ph.D. is working on this. The postdoc working is in the DeepAir. And what we would like to go is into the haze event for us in California would be fires. So that's what I expect to do, causal inference to begin with fire, and later better quantitative understanding of the emission inventory. So this is a long path, but it's very interesting because it combines environmental data with human activity, and that is what we would like to do. In the Outlook, it's very important to connect the link, and the conclusion of this part is that AI can support better understanding of human natural system at a global scale. So I show you everything about air quality, but we hope that there are other type of climate-related research that can be done with that. So I told you two completely different topics, one that is mature, one that is 1.5 years old. And given the audience that probably are the people working on aviation data science, I wanted to take few comments, it's only 3 slides, about some perspective on aviation data science. And let me start with this review paper that I found fascinating, that is by Banavar. He's from this lab. Wow, so here he says in a very nice way, what are all the data that is available, the type of applications that we need, and he goes in some aspect of how to do that. So for me, so here is basically all the content based on his experience. Data science, aviation data science class should take some of these aspects and leverage on that, in which students learn how to get access to this data, apply methods, and try to tackle some of the applications. So in the classes, you can learn the methods, project-based, very interesting things can happen. So the data is there. I did everything about urban mobility or air sciences. Aviation data science from the perspective of new data science type of methods, less so. So I do believe, and I am total supporter of such classes with NASA Ames and Berkeley. So my only take, my only experience in aviation data science is this data that was used for one of the students in my lab long time ago. Here we have the data that is collected by the aircraft. So every user, we know from where to where they go, and then you can track individual planes with people that go, let's say, from LAX, Honolulu, JFK, so on and so forth. What is an incredible application that not necessarily is tackled at NASA now, but this data is used for, is epidemic spreading. Right now for the coronavirus, if you see CDC prediction, the way they are really prediction, the way they inform not to let my postdoc Yan that is right now in China, he cannot come back because he stayed in China more than 14 days. He's stuck there is because the trips are stopped and the whole epidemic modeling uses the information from the traffic of air. So the data is purchased, is used for research purpose. In this small paper, what we did is showing that non-trivial airports, let's say like Hawaii, would have a boost on the epidemics, meaning they don't have too much travel at JFK, but because they go to Asia, and depending where you go, you can do a network metric. This is a metric of influential spreading. Whoa, wow, it's 2012. Sorry, it's a typo, but 2012 is long ago, as I told you. So basically, you can use he did the movie from before, we convert the network of mobility, we run the epidemic spreading, and we show a non-trivial result about the very first 5 days. Some airports have more boosting power than others. A lot of work is done today to be forecasting the epidemic for any new epidemic that comes in our way. And that, of course, is the experience I have because I work in socio-technical system, and epidemic spreading belongs to complex system research. Now, This is the last slide. If we think about the urban air mobility, one aspect is knowing the demand, of course. I show you that the demand is useful and you can predict the impact of adoption of EV. You totally can predict the impacts of the adoption of urban air mobility and how it's going to affect energy. That is a work that I'm sure several people is doing already. One aspect from the city science perspective is see how complex cities are. So not only in the density of population on the ground, the city texture is so different. And if you're going to have the small, well, of course, there are two types of urban air. One is transporting people, vertiport, that is a big one. But the ones that is going to be for logistic, drones-like, you have the urban canyon. So we really need to have a very good flavor of the city texture to plan for the landing. And in that realm, I'm putting here a street maps patterns. It's just beautiful picture by Jeff Boeing. And I want to point out that as OpenStreetMap data on the street over the planet we are used to, go to this webpage. Microsoft released the building footprint in the entire US. 100 million of buildings in the entire US. Then, here is a Ph.D. I was part of the committee. It's a PRL, so it still is physics style, but his role of city texture in heat islands at nighttime. But his second part of the research was on the urban canyon. So this type of approaches in which you check which city we're talking about. What is the texture? And by the texture, we mean the height of the building and how they are, the organizational patterns. How many people are there? Right now, we have all this data available. Instead of the micro simulation, you can think this type of view is like the thermodynamics. It's mesoscale, but it still is very useful for the planning perspective. And with that, I would love to give you some time for questions, discussions, and anything you would like to talk to me. Thank you very much.
I have a question, Marta. So some of the stuff that you talked about for the electric grid, so one problem which is analogous in the aviation world now coming up is what I see is the charging of aircraft near vertiports, right? How transferable do you think are those methods to a problem like this, where the data even doesn't exist at all right now?
Yes. The details of the unknown is the challenge, so that is not transferable, the unknown. However, the methods very much so. So we can do the demand. It was probably, see, my PID, you know, the way I inferred the adoption of the current vehicle. So notice I inferred the current ones. In the vertiports, probably, well, rarely. We don't have even 0.65% of people traveling through that. However, one of the aspects I would like to bring into the table, now that we have data and all the map revolution, we can have our commuting of one of the complex in California, LA. We can have LA, and then we can do a scenario analysis. It's going to be okay. We are not predicting who the vertiports are, but we can do the scenarios and see very well the charges, because what we have correctly is the numbers of the demand. And then a scenario is one start, I think. And then we can do recommendations such that we don't need to give the recommendation after they adopt it. We can inform regulation. That's the part of thing I think it will be very interesting.
So these city textures, it's interesting, right, because they're so unique. And however, right, when you talk about drone applications, what most likely is more important is these like wind fields that are like flowing between buildings and stuff like that. And moreover, it might be good to have some type of prediction, you know, that's like static in the future, but you really need like a real-time prediction to inform these drones. And so is that something you can actually see going from talking about just textures of buildings to like what's the roadmap to get from just like this is a map of buildings to a real-time prediction of like wind fields between buildings?
Yeah, thank you very much. I, on purpose, put this as the last slide. You're absolutely right. This was my attempt, my cheap attempt to tell you that the wind field matters, and where I meant the wind canyons. So the urban texture equivalent is if I tell you, like with the road map, with the road network of OpenStreetMap, you are going to tell me the traffic model. Definitely not, right? So the provocative view is, as we had OpenStreetMap that revolutionized, right now everybody do traffic models, they use OpenStreetMap data type. Then what I'm saying here is we have the urban texture. To our problem, wind maps, very much into NASA type of data, needs to be informed. And of course, it's the simulation in which you have the wind. That's my point, is do not stay in one city because the textures are going to be so different that once you calibrate one model, you can go to others. And that is going to tell you one component of what place is like a map, where you should know, you should, and somehow having it. Then the population maps are there. We have either phones or no phones. The drones are going to have cameras. They would not likely need my estimate. What I was thinking on what is useful for me to real-time, a drone looking of where they are is the most important. It's equivalent of the self-driving car. The self-driving car would not use my model necessarily, that he's going to be aware of what's going on. However, to deploy the self-driving car from Uber, you need to decide which places would be started. So the model of how many people you have on the city texture with the wind is like the map that is going to try to do the scenario where we would get started with a new technology. It means we are not going to get started perhaps with the autonomous cars in Manhattan, but there are some places in Missouri that maybe we do. That aspect of, because at the end of the day, this is a lot driven by business, and some part of that we can do is, given all the requests of Amazon, which fraction of them can be served through drones. So this is one layer of quantifying things. It's not the only one, because the key component, as for self-driving car, is control, which is not my area, but it's another layer. So if we work together, we build cases in which we show how we can go from an idea to something on the ground, including the business model out of this. That's my view.
Marta, I have two questions. One is the Microsoft US building footprints. Are they just images or okay, just images, right?
No, good question. Are only footprints, which means the footprint and not the height for the entire planet. So there are some building codes. If you know the footprint, you can imagine and estimate the height. Manhattan, Chicago, few cities, you have it all, 3D. It's just because the city has, and with this open data source from the city, they're providing this. The customers of these 3D building maps is in architecture and energy, building energy. To do the simulations, you need the perfect information on the building. Not only the shape, the materials, the number of windows, energy plus type of simulation. Many cities have it, but by the time we have it all, we don't. We only have the footprint, and then you can assume. So you can learn a statistic on the texture, because in fact, there is building code. You cannot have all buildings of a big height. So good point, thanks. It's just starting, not all of them are in 3D.
Okay. But the footprint itself is a geolocated area, right? So it's not just an image, it's actually a point which you can drop a pin on.
Yeah, absolutely. From the GIS perspective, it's a polygon like the streets are. So it's a GIS thing that you can download and work with it. Okay. It's more than an image. Yeah, it's a GIS.
Okay. The second question I had was, that how far in advance can you predict haze or something like that?
That's such a good thing. My goal is 1 week before. And as I told you right now, what I'm going now is what we have is 90% training, 10% testing, and I am at the day in a place checking if my prediction goes with a monitoring station. That is what I call a spatial prediction. Temporal is the one we want to go 1 week ahead, because the haze event lasts 1 week. Yes, it's two things. Temporal is the ideal. Right now, I only have a spatial. One thing that you need to be not trusting is when they gave you cross-validation, which means 90-10 within the same time period, so you're not doing neither spatial nor temporal, it's a regression. So that's the one you need to not do. At least either spatial or temporal. Right now I'm only in the spatial, which means in these places, I only have the data, weather data and the maps and all the layers. I can predict what the monitoring station at a daily basis.
Okay. Thank you.
Berkeley.
Thank you for the question.
Any questions at Berkeley?
You have a question at this end.
No.
We can't hear you.
Maybe no questions there.
I think someone has one, they just don't have a mic. There we go.
Okay,
Function, I think you have your laptop mic on instead of the USB mic, because I can hear you.
okay. Sorry.
Or maybe you can just repeat the question with
Yes.
the mic that's active.
No. Oh, yeah, you troubleshoot it next time.
No.
Could you
Yeah.
just repeat the question from the laptop
Well, then,
microphone?
Yes, we're gonna repeat the question in the computer microphone.
Okay.
Oh, no, I don't hear it. Text it to me. Tell Raya
We
to
can
text me the question.
Hello?
Yeah.
Conference I have for this.
It wasn't much more of a question, but more of a comment that I believe the wind fields within the city, various city textures would be very interesting, not just relative to airflow, but also relative to temperature gradients. Since most of the drone technology these days are rotary wing versus fixed wing, I believe that temperature has more significant, air temperature is a significant factor in terms of lift dynamics on the rotary mechanism, such that that may have an effect in terms of load versus energy required to fly through, let's say, New York City on a hot summer day. That could impact that. I know that, for instance, in LA, when they're doing search and rescue through the LA County canyons, that they do factor that into situations because there was an accident along those lines when a helicopter crashed because they loaded too many people under hot weather conditions.
Wow. Thank you. Thank you very much for the comment. And I'm so glad because it's somehow, I wanted to bring that message and I talked to David about it. It's like, it's not what I did. So I could not talk to you the entire amount of time about it. My point in urban air mobility is that it needs know-how beyond the transportation and planning, that is my real hat, is because according to what he said on the wind maps and the temperature, it's not necessarily the people from transportation planning is going to do it, but we have fluid mechanics, we have aeroastro. So part of the message I wanted to bring is that there are challenges that combine the physical infrastructure with the wind and the temperature, absolutely unique to make. And in the spirit of my first slide, we have all these layers that is data informed. So if you ask me the amount of people I believe is going to be there, we are that layer. But then it have to be, let's say, in New York or in LA, wherever we go, we have other aspects, everything to be done. That's why I like that it captured your attention because that's why I am a believer that this class can be very important. There's many things to be done in this field. And yeah, that's where I came, even if when they invited me, I have not much to say about air mobility. Well, I can tell you about data science and urban mobility.
I was just going to say one comment would be that, you know, this idea of urban air mobility is new and exciting. However, there might be a more obvious connection of your research to aviation, which is door-to-door commutes. And so that's a big question, which is that, right, there's a lot of your travel time, depending on where you're coming from and where you're going, which is just getting to the airports, getting through security, stuff like that. And I think, you know, the Department of Transportation and stuff appreciates this flavor of research of door-to-door commutes because I believe in Europe, that's kind of more the focus of their research, whereas we just look at like air travel time and stuff like that. So that might be a more natural way to like integrate that work kind of more immediately.
No, absolutely. Those are, I have, for example, Ferrovial. There's a corporation, a Spanish corporation that handles airport. Heathrow is handled by Ferrovial. So those type of collaborators I have very well. And particularly, you say it, in Europe, they really pay attention to that. In the US, the thing is, because I came with a very new techniques, and you see TRV, so huge. It's just a matter of time. I work more into door-to-door transportation US. There is so much in control of highways. I don't do control of highways. But you're absolutely right, and that I am aware of, and I have been funded, who funded my projects, Ferrovial, Ford, BMW. People that is interested in the mobility business, and they want a fast model, data-driven, and even their customers are with us apps. All that is absolutely true. I mentioned the flight data because it's less available to us to combine the worlds. And definitely on this because it's to be done to the future. But you are right, absolutely.
I have a question regarding collecting the data itself. Are you able to access those data free, or do you actually get charged for using the data? For instance, with the wireless mobile communication operators, as an example, are they willing to provide those sort of data to the community?
Yes, this is a big elephant in the room. The usual providers, the originals I had is mobile phone companies, Sprint, Verizon, that they have a spin-off, like AirSage, that I mentioned in one of my slides, is AirSage. This is triangulated mobile phone data. If you saw New York Times articles in which they show people in the Pentagon and how the smartphones can really locate people everywhere, that's this data. I'm not a fan of the New York Times because it captures attention, it slows down the process, but they were right in the article. This data is there and we only need to buy it, of course. They are not going to sell if you don't treat this like human subjects. It's available for purchase, and now the situation is much better than when I started. There was only mobile phone providers. Now it's people with the apps. Of course, you are only mapping the people that have smartphones, but as I told you, you correct for the people you don't have. The data is never perfect. It requires some work. It's more available, I would say. So it's public, they have their webpage. It's not only one. This is one I work with, the data I'm showing here. There are several more.
Given the time, I think we should thank Marta.
Thank you.
And she'll be available to talk after.
Thank you.
Also, if you were looking for feedback on the seminar series itself, if you search USRA Aviation Data Science, at the bottom of the seminar series page, there's a feedback form linked to it. So we appreciate any feedback you have on the series. Thank you.
Thanks for people at Berkeley, I guess.